So now we're looking at the 2012 free response question number 5. And we have a problem here that involves a baby bird gaining weight. And the first thing that should stick out to us right away is that we have a differential equation, dB dt. And you could probably see where this is going. We have the differential equation which gives us the rate at which this baby bird is gaining weight. What we don't have is the equation b of t, which would then give us the weight of the bird at any given time. But as you can probably figure out, we'll get there. So let's start with the first part. The first part is asking, is the bird gaining weight faster when it weighs 40 grams or when it weighs 70 grams? So we are going to use dB dt. So let's look at this first part. So we have dB dt, and we are going to evaluate this differential equation when we know that its weight is equal to 40. So B is going to give us our weight, so at 40. So from here, we're just going to plug in B being equal to 40, so that's 100 minus 40. So 1/5 of 60, then just gives us 12 grams, right? And this gives us grams per day. That's the weight at which this bird is growing. Now let's look at dB dt at B is equal to, what was the other weight? 70. So then we're going to say 1/5 of 100 minus 70, 1/5 of 30, and we can just see that that is going to be 6 grams per day. Well, dB dt here, we can see that dB dt at B is equal to 40 is greater than dB dt when B is equal to, and I should probably fix that, B is equal to 70. Let's clean that up just ever so slightly. FRQ, we want to be neat with our work. Therefore, we can see that the bird is gaining weight faster when it weighs 40 grams. Just write that underneath. Okay. All right, so that's the first part. So we were able to figure out the bird is gaining weight faster when it weighs 40 than when it weighs 70. Now in the second part here, they're giving us this second derivative, or they want us to find that, but what they are giving us is a possible graph. So the first thing we want to find is this second derivative, or the second differential equation, and we want to explain why this graph here cannot resemble what the actual graph of B is. Well, let's first look at what this second differential equation would be. So we're going to say d2b t squared. And what we're just going to do is we're going to start by finding the derivative of this first equation up here. Well, if you just look at the derivative of that, we have a constant, we have a negative coefficient inside our argument. So just using the chain rule, we would just have negative 1/5 dB dt. And we know what dB dt is. So we're just going to go ahead and write that in. We've got negative 1/5 times 100 minus b. And we have negative 1/25, 100 minus b. Okay, so we have our second differential equation. Now it's asking us, what do we see about this graph, and can we determine whether or not this could actually be the graph of B? Well, looking at what we found here, we see that when our B value is less than 100, okay, so when our B value here, our weight in grams, is less than 100, then we see that dB dt is going to be, our second differential equation is going to be less than 0. It's negative, which means it's got to be concave down. So let's write that. When B is less than 100, this is negative, therefore it's concave down. However, if we look at our graph here, clearly there's a portion of the graph that's actually not concave down. In fact, the majority of this graph, when b is less than 100, is concave up. So we can then say part of the graph however, is concave up. Therefore, the following graph, or let's just say the graph cannot be the graph for B, okay, for equation B. All right. Now, our final part here is the part that everyone should have seen coming. Given this differential equation, we're going to use separation variables here to find our actual equation. So remember, that's typically what we do with differential equations. We're saying, all right, can we find the solution to this differential equation, which means can we find the equation whose derivative in this case would be dB dt? And they are giving us an initial condition of b of 0 is equal to 20, which means we're actually going to need to solve for a constant that we're going to get using integration. So the first thing we're going to want to do anytime we solve a differential equation is to actually separate the variables. This is a separable equation. So we're going to move all the b terms to one side and the t terms and any other constants or coefficients to the other. So from here, we can just go ahead and write this as, what do we have here? dB over 100 minus b. And over here on this side, we've got 1/5 dt. Okay. Now, if you want to, you could actually factor out this negative that you see here now. That way you don't deal with a negative later when we're actually integrating, but it's not that big of a deal. So from here, now that we've separated our variables, we've got the b terms on one side. We're going to go ahead and integrate both sides. So looking at that here, this is going to give us, remember your rules for integrating with natural log. So we've got the natural log of 100, or I should say the absolute value of 100 minus b. And since the coefficient in front of b, I left that alone, it was negative. So this is going to be negative natural log of absolute value of 100 minus b. This here is just going to give us 1/5 t. And let's just go ahead and add that constant now. Okay. So we separated the variables, we integrated both sides, and now we can either continue to solve for our b value or just write all in terms of b is equal to all values in terms of t, or we can actually solve for a constant here as well. It's up to you. You can. I'm going to go ahead and actually do a few things before I exponentiate. I'm going to go ahead and move that negative over so that I'm not dealing with a negative ln. And then I'm going to go ahead and exponentiate all that. So we're just going to go ahead and just do this. Negative of all of that. And from here, I am going to now exponentiate both sides. And that's going to give me 100. Oh, and I should point something out about this absolute value of our argument here. So if you look here, you'll notice that we have the absolute value of 100 minus b. But because b is going to be, as was given in the problem, b represents values between 100 and the lowest it got to was 20. Since we know that this is true, that means we just really need to deal, we can just work with 100 minus b. We don't have to worry about the absolute value, right? We always know that b is going to be positive. So we have 100 minus b, exponentiate this side. This is where you might want to say let, and be careful with our constants here. Let's call that c1. Let's call e to the c1 here equal to c. Okay, so then we can write this as e, or c, I should say, big C, times e to the power of negative 1/5 t. Okay. Now from here, we can go ahead and solve for our constant. What was the initial condition that was given to us? We saw that b of 0 is equal to 20. Therefore, we can say since we know that t is equal to 0, when t is equal to 0, b is equal to 20, so we can say 80 is equal to c to the e to the 0 power would just be 1, so we know that our constant now is equal to 80. So from here, let's go ahead and move b over to one side by itself. So we're going to say 100 minus 80 to the e to the negative 1/5 t is equal to b. And there's our equation. Ooh, that's a horrible box. Okay?